So in this lecture, I will discuss the central limit theorem. So we have already seen that if we have a sequence xj of iid random variable, such that the expectation of these variables are equal to 0 and the variance of these variables is finite, say equal to sigma square, then by using the characteristic function, we proved that x1 plus xn divided by square root of n converge in distribution to the Gaussian random variable with mean 0 and variance sigma square. So this we proved already as an application of the characteristic functions, but what I want to discuss today is that we don't need these random variables to be independent. So in this lecture, we will consider, so let me write, again, from scratch, xj, a sequence of independent random variables. I will assume that these random variables have mean 0. And I will represent by sigma j square the variance or the expectation of xj square. And what we would like to prove is, say, if I take Sn square as the sum of sigma j square from 1 to m, then if I sum x1 plus xn and I divide that by Sn, where Sn it's given, Sn squared it's given by the sum, you see that this random variable has mean 0, and since these variables are independent, the expectation of the square, so the second moment or the variance of this random variable, will be given by 1 over Sn square multiplying the sum from 1 to n of sigma j square, and this is 1 by definition of Sn. So we have here a sequence of random variables with mean 0 and variance equal to 1. So under which conditions this sequence of random variables converge in distribution to a Gaussian which has mean 0 and variance equal to 1. So the main theorem of this lecture will be that the Lindbergh condition is sufficient, and the Lindbergh condition reads as follows. Well, we will assume that 1 over Sn square of the sum from 1 up to n, or the same n, the integral for x larger than epsilon times Sn, x square d mu j. So mu j here is the distribution measure of the random variable xj. So I'm integrating that for all x whose absolute value is larger than epsilon times Sn, the same Sn. And I will require that this converge to 0 for all epsilon positive. So that will be my assumption. So the main theorem of this lecture will be to say that, well, the sequence of random variables converge in distribution to a Gaussian with mean 0 and variance 1, provided the Lindbergh condition holds, which is written here, that here for all epsilon, if I integrated x squared d mu j on the interval at which x, the absolute value of x, is larger than epsilon times Sn, I sum that over all j from 1 to n, and I divide that by Sn squared. If this converges to 0, then this result holds. So here I wrote again the statement of Lindeberg Theorem. So the random variables are independent, they have mean zero, they have finite second moment. I'm representing by Sn square the sum of the second moment. I forgot to say that I'm assuming that Sn is converging to plus infinity. And then we have Lindbergh's condition, which reads as 1 over Sn square times the sum from 1 to n of this integral converge to 0, where mu j, again, it's the distribution measure of the random variable xj. Then x1 plus xn divided by Sn, it's converging in distribution to a Gaussian random variable, which has mean 0 and variance 1. So before I prove this theorem, let me present some consequences of this assumption. So my first claim is that the maximum of sigma j square divided by Sn square, and the maximum it's taken from 1 up to n, that this converge to 0. So if I take the variance of, or the second moment of the jth, and I divide it by Sn square, this is converging to 0, and even if I take the maximum over all these variances. So let's prove this statement. So let's remember that xj square, it's the second moment, so this is equal to x square d mu j. Now let me divide this integral in two pieces. So let me fix an epsilon positive, and let me write this as the integral for x smaller than epsilon Sn, x square d mu j, and plus the sum for x larger than epsilon Sn, x square d mu j. So since x it's bounded by epsilon Sn, x squared is bounded by epsilon 2 Sn square. So and this integral now is bounded by 1, because mu j it's a probability measure. So this is bounded by epsilon 2 Sn square. And well, and this expression, well, I'll just bound it by the sum. So I'll bound that by the sum from 1 up to n, x larger than epsilon Sn, x square d mu k. And therefore, if I divided xj square by Sn square, what I get is that this is bounded by epsilon square plus 1 over Sn square times this sum. And you see that the right-hand side does not depend on j anymore. So this is true if I take the maximum for j between 1 and n. Now I can use Lindbergh's condition, which tells me that for all epsilon, this quantity here converges to 0 as n goes to infinity. And from that, I deduce that the limit as n converges to infinity of the maximum for j between 1 and n of sigma j square divided by Sn square, that this is bounded by epsilon 2. And that's it, because, well, now I can send epsilon to 0 to get that indeed this maximum converges to 0 as n goes to infinity. So my second claim is as follows. So if I have a sequence yn, remember that yn converges to 0 in probability if for all epsilon positive, the probability of yn to be larger than epsilon converges to 0. So that was the definition of convergence in probability to 0. So now let me define, and this is a notation which I will use in this lecture, x and j to be the random variable xj divided by Sn. Because with this notation, I can represent this sum as a sum from 1 to n of x and j. And it's this sum which I want to show converge in distribution to a Gaussian with mean 0 and variance 1. So let me introduce this notation. And now what I claim is that, well, if I take the probability that x and j larger than epsilon, and I sum that over j, I claim that these converge to 0 as n goes to infinity. So you see, well, it's a very strong statement. It's telling you that, well, each of these random variables converging to 0 in probability, but actually more than that, because we can sum over all this probability, and this is still going to 0. So it's this Lindbergh condition implies that each of these variables is really small. It's converging to 0 in probability, but more than that, there is some uniformity in J in this convergence to 0 in probability. Well, and why is that true? Because, well, that sum, it's less or equal, so you can apply Chebychev inequality to say that this sum, it's bounded by x. So let me recall that this is xj divided by Sn. Let me put Sn together with epsilon. And now let me apply Chebychev inequality. So this is larger than Sn. And here I have x squared divided by epsilon square Sn square d mu j. So this is just Chebychev inequality where I keep the set. So remember, usually in Chebychev inequality, you ignore this set. But let's now this set. So we have that sum. It's bounded by this one. And this one, well, I can rewrite it as 1 over epsilon square, 1 over Sn square, the sum from 1 to n of x larger than epsilon Sn, x squared d mu j. And this, by Lindbergh's condition, converges to 0. So indeed, we proved the second claim, and which I repeat is telling you that these variables x and j converge to 0 as n goes to infinity, but in some sense uniformly over j. The proof of this theorem will be based on, we'll use the characteristic functions. So what we will prove, we will show, is that if I consider the characteristic function of x1 plus xn divided by Sn t, that this will converge to the characteristic function of a Gaussian mean 0 variance 1 of t, and this we know it's exponential minus t squared divided by 2. So what we'll prove is that for all t, we have this convergence. Now, well, here we know that since the random variable x1, xn are independent, this is equal to the product of the characteristic functions of xj divided by Sn. So I'll just write it here, xn, in this way. And now, in our case, this is j equal 1 up to n of f xj of t divided by Sn. Right, xn over j, it's xj Sn. And we have seen that the characteristic function, well, we just can place a constant inside the function. So now, well, we know that fxj of, let me call that r, since we have a second moment, we have seen an expansion of this characteristic function. So this characteristic function, I'll just remember, it's 1 minus IR, the expectation of xj, minus plus plus IR square divided by 2, the expectation of x1 square, and plus delta R, in which delta R, if you remember from the lecture in which we proved that, it's bounded by 4 times the expectation of x1 square. And this is for all R. So here, since the expectation of xj it's equal to 0, this term is not there. So we have 1 plus, here we have minus. This is why I mixed d minus. So minus, here we are computing a t Sn square. So minus 1/2 of t Sn square sigma j square, because this is the expectation of x1 square, and plus dr, which is multiplied by r square. So plus dr times r square, but dr it's bounded by 4, so plus an error. And this error in absolute value, it's bounded by r square, but r square it's again t divided by Sn square. And then we have 4 times the expectation sigma square, which is sigma j square. So our expansion gives us that fxj with at t Sn, it's equal to 1 minus this quantity, and therefore this tells us that phi xj t divided by Sn minus 1 in absolute value, this is bounded by t square, a constant, sigma j square Sn square. So the conclusion of this computation, well, this expansion, is that phi xj at t divided by Sn minus 1, it's bounded by some constant which does not depend on t, on j, or on n, times t square, sigma j square, Sn square. And we have seen that, well, this is bounded also. So let me continue to write this here. So I'm continuing here saying that, well, we have seen that the maximum of these quantities converge to 0. So this is bounded by C0 t square an, where an it's equal to the maximum from 1 to n of sigma j square divided by Sn square, and this converges to 0. And this holds for all t bounded by t. So we just proved the following bound, which will be very useful because you see that we are here expanding, well, these characteristic functions appear. The way in which we'll prove that it converge, it's by doing an expansion, and these bounds tell us that this the characteristic function, it's close to 1 by an error which is uniform over t and over j, bounded by a constant which vanishes as n tends to infinity. So let me write that here. We proved that the maximum for 1 j n of phi x n j of t minus 1, and if I take the supremum for all t less equal than t, that this is bounded by this quantity, by a constant, a universal constant, times t squared times an, where an is this quantity which vanishes as n goes to infinity. So this quantity here can be made as small as we wish by taking n sufficiently large. And that will be an estimate which will be used many times in this proof. So we are now in position to prove this theorem. And as I said, the idea is to show that the characteristic function of x1 plus xn divided by Sn of t converge to the characteristic function of the Gaussian random variable with mean 0 and variance 1. So, well, to prove that this converges to that, let me take the logarithm and show that the logarithm of this expression converges to that one. So what will be of interest here is that the log of this quantity minus the log of exponential minus t2, which means that we want to estimate this quantity. So we have seen that this quantity, since the random variables are independent, and by definition of x and j, and you will see at the end of the proof why I'm sticking to this notation, so that this is log of phi of the sum of x and j from 1 up to n, t plus t squared divided by 2. So this is the quantity which we want to show converge to 0. Since these random variables x and j are independent, the characteristic function of the sum is equal to the product, but we have a logarithm here, so that becomes the sum from 1 up to n of the logarithm of phi n j of t plus t squared divided by 2. And phi n j means phi of x and j, which means the characteristic function of the random variable nj. And we have seen, that this is close to 1, so I want to rewrite this logarithm as an expansion in 1. So this is sum from 1 to n. Here, what I will do is I will write that as 1 plus phi nj of t minus 1. Then we have plus t squared divided by 2. And what we have seen here is that this quantity, and if I take a maximum and a supremum over t, it's bounded by, so this quantity here, it's bounded by constant t squared an. And as I said, an converges to 0, so I can make this expression smaller than delta by taking n sufficiently large. And now I can use the expansion, so log of 1 plus z. So here z, it's a complex number. But if z, the modulus of z is small, this expression and the modulus of this expression, it's bounded by a constant times z squared. So I want to use that for all, so z less or equal than delta, z a complex number whose modulus it's bounded by delta. Then I want to use this expansion to write the sum. So I have here log 1 plus z, and this is our z. So I will subtract z, and add z. So z, it's phi n j t minus 1 plus t squared divided 2 plus an error. And this error in absolute value, it's bounded. So we have log 1 plus z minus z, so it's bounded by a constant. So we have a sum. from 1 to n, and this expression, constant, times z, in our case it's phi and g, minus 1 square. Right, so up to now, we wrote this difference as this expression plus an error which is bounded by this expression. And so my next step will be to show that this error converges to 0. So that will be one part of the proof. And then show that this first term also converges to 0. So I will just erase everything, keep this sum, show that it converges to 0, and then show that this expression converges to 0. So this is the first part of the proof. We need to show that this sum converges to 0. So what we will do is that we will estimate this by the maximum of j between 1 and n of phi n j t minus 1 times the sum of phi n j t minus 1. And so now what we claim, so this part 1 will be divided in two, claim 1 and claim 2. Claim 1 is that this first piece converges to 0, in the sense that if I take the limit as n tends to infinity of the supremum for t bounded by t, the maximum between j from 1 to n of phi n j t minus 1, that this goes to 0. The limit is equal to 0. And then the second claim is that the supremum for t less than t of the sum of phi n j t minus 1, that this is bounded by a constant t, which does not depend on n. So if you are able to prove that this term converges to 0 and this one is bounded, we get from this bound the first part of the proof. So we have two claims to prove in order to prove part 1. So here is claim 1. So follow closely, because the arguments used in claim 1 will be used also in claim 2, and I don't want to repeat them. So phi n j t minus 1. So remember, phi n j is the characteristic function of x and j. And x and j, it's xj divided by Sn. So I can write this as the integral of exponential I t x divided by Sn minus 1 d mu j. Right, this is the characteristic function of xj divided by Sn. Now I can use the fact that the expectation of xj is 0 to rewrite, to introduce in this integral the linear term. So minus 1 minus I tx divided by Sn d mu j. Well, because this integral is equal to 0, because xj has mean 0. Now I can place the absolute value inside to say that this is bounded by the integral of exponential I tx divided by Sn minus 1 minus I tx divided by Sn d mu j. Now let's use the following bound for the expansion of exponential I theta minus I theta, so that this is bounded by a universal constant times theta square. So I leave it to you to check that this bound holds, so that exists a universal constant C0 for which this holds for all complex values theta. So by using this inequality here inside, we get that this is bounded by constant. And here what appears, it's t square, x square, Sn square, d mu j. And, well, now x squared d mu j, it's sigma j square. So this is bounded by constant. T square, it's bounded by capital T square. Sigma j square divided by Sn square. And this is bounded, well, it's not bounded, but I estimated here this expression by this term. So now if I take the maximum for j between 1 and n, I get that this is bounded by C0 t square, the maximum for j between 1 and n, sigma square Sn square. And we have seen at the beginning of this lecture that this quantity converges to 0 as n goes to infinity. So indeed, the supremum of the maximum of g of this absolute value converges to 0 as n converges to infinity, and this completes the proof of claim 1. And as I said, claim 2, the proof of claim 2 is very similar. So claim 2 is that the supremum of the sum now it's bounded by a constant t, which does not depend on n. So we repeat exactly the same expression in order to bound this quantity. This is equal to that, which is equal to this. We introduce itx in this expression because xj has been 0. We place the absolute value inside. We use the expansion, the Taylor expansion of exponential I theta to bound this quantity. And so we reach that this absolute value is bounded by this quantity. And now I'll say that this is bounded by a constant 0. Then t, it's bounded by t square, as before. X square d mu j, it's sigma j square. And this is divided by Sn square. So now, if instead of taking the maximum, I just take the sum of xj square, it's exactly equal Sn square. And so what I will get is that this quantity here, the supremum of the sum, it's bounded by constant 0 times t square. And this is exactly what we wanted to prove. And so putting claim 1 and claim 2 together, we have part 1 of the proof. And therefore, to complete, we only need to prove part 2. So now it remains to complete the proof to show that this estimate holds, which is part 2, so that the supremum converges to 0. And here again, so let me consider the absolute value of this sum. And write phi njt. For phi nj, remember, it's the characteristic function of the random variable x and j. So as before, I will write this as the exponential itx divided by Sn minus 1 d mu j. And then t square, let me write t square. So if I divide this sum by Sn square, I get 1. So I will write this one in terms of this sum. So that will become t sigma j square 2 times Sn square. And now the sum concerns this term. So we have a sum of all these terms. And here I left a blank space because I know that the expectation of xj is 0. So I can add here minus I t x Sn. And I can also remind myself that sigma j square is the integral of x square d mu j, to replace this sigma square by this integral, and therefore what I have, it's a t and t square, I'm sorry, here it's t square divided by 2sn square. So this term will become that one, and I will put this term inside the integral, so this is equal to the absolute value of the sum of the integral of exponential I t x divided by Sn minus 1 minus I t x divided by Sn, and then plus t. Now is this integral, so t square x square to Sn square. And now, once we reach this point, I will divide this integral in two terms. The first term, I will consider points x which are bounded by epsilon Sn, and the terms x which are larger than epsilon Sn. So here I fix an epsilon, and I consider this integral in these two pieces. So I'll first estimate the first one, and then we'll turn to the second one. So for the first one, so remember that epsilon has been fixed. For the first one, I will simply use the expansion of exponential I z up to the third order term. So you see what's appearing here, it's the expansion of this function. It's one linear term and the second order term. And we know that exponential I z minus 1 minus iz plus z squared divided by 2, that this is bounded by a constant 0 times z cubed. For there exists a constant c0, such that for all complex numbers z, this inequality holds. So for this term, I'll first place the absolute value inside the sum, then inside the integral, then I will use that bound to estimate this term by the sum from 1 up to n of x bounded by epsilon Sn. And here I have a constant c0, which is coming from this expansion, and z here it's tx divided by Sn. So this is t cube x cube Sn cube d mu j. Well, t, it's bounded by capital T. So this is bounded by c0, capital T to the power 3, the sum. And now I have x cube Sn cube. One of these factors, I will use this inequality to say that x divided by Sn, it's bounded by epsilon. So I get an epsilon, and then remains x squared divided by Sn squared. Once I replace the first one and the second power remains, I will just forget this restriction. The second power integrated with respect to mu j will give me sigma j squared. So this is sigma j squared divided by Sn squared. And by definition of Sn squared, this sum is equal to 1. So we proved that the first term is bounded by constant t cubed times epsilon. So this is a bound for the first integral. So keep it in mind that we proved that it's bounded by a constant t cubed epsilon. And now let's estimate the second term. In the second term, so let's forget the first one. In the second term, I will use the same approach. So I'll place the absolute value inside the integral. But now I'll consider separately these two terms. And the first one, I will use again the Taylor expansion. but now up to the first order to say that exponential iz minus 1 minus iz, so that this is bounded by a constant 0 times z square. So, and this one I will keep it as it is. So what I have is that the second term, it's bounded by a sum from 1 to n. The integral from x larger than s epsilon Sn. Now I have a constant c0. Z here, it's tx divided by Sn. So that gives me t square, x square, Sn square, d mu j, plus the second term, which is exactly the same, but instead of c0, I have a 2. So this is bounded by a constant plus 1/2. T square, it's bounded by t square, capital T square. And what remains is 1 over Sn square, the sum for j from 1 up to n of the integral from x larger than epsilon Sn, x square d mu j. And this is exactly Lindbergh's condition. This Lindbergh's condition tells me that this expression converges to 0. Therefore, if you remember now the first term, we proved that this expression, it's bounded by a constant times t cube epsilon. So that the limit of this expression, it's bounded by that. Since epsilon, it's arbitrary, we can send it to 0 to get that this supremum indeed converges to 0, and this completes the proof of Lindeberg's theorem, so that under these assumptions, indeed, these sum converge in distribution to a Gaussian with mean 0 and variance 1. So to complete this lecture, I want to make 2 observations, 2 remarks. Remark 1, which is called the Lyapunov theorem, is as follows. Suppose that there exists a delta positive such that 1 over, with the same notation, Sn2 plus delta, the sum j large from 1 to n of x 2 plus delta d mu j converge to 0. Suppose that this limit is equal to 0 as n goes to infinity. So assume that there exists a delta strictly positive for which this limit is equal to 0 as n goes to infinity. Then I claim that Lindbergh condition holds. Here, well, I didn't make it clear, but I'm assuming that xj are independent random variable with mean 0, and I'm assuming this condition. So assume that xj is a sequence of independent random variable which have mean 0, and that this condition holds where Sn squared is given by this expression. Now I claim that in that case Lindbergh condition holds, and well, that's easy because we want to estimate Sn square of the sum from 1 to n of x larger than epsilon Sn of x2 d mu j. We want to show that for any epsilon these converge to 0. So fix an epsilon. Well, consider that sum. Here, this means that 1, it's less or equal than x divided by epsilon Sn. And therefore, 1, it's also bounded by x epsilon Sn to the power delta, where delta is the one appearing here. So I can here estimate 1, which is multiplying x squared, by this quantity to say that this is bounded by 1 over Sn squared, the sum from 1 to n. X here appears then to the power 2 plus delta. We have here an epsilon to the power delta and Sn to the power delta d mu j. This Sn to the power delta gets outside of the sum to give me a plus 2 delta. And now I can also remove from the sum the epsilon to the power delta and apply Lyapunov condition to claim, of course, once I estimate 1 by this quantity, I can just forget about this restriction of the integral, and therefore this is bounded by this expression. By Lyapunov condition, these converge to 0. So Lyapunov condition, it's stronger than Lindbergh condition. In particular, if you have a sequence of independent random variable with mean 0 and satisfying this condition, then you have a central limit theorem for these quantities. So, and this is called Lyapunov theorem. So, final remark, and this is also an exercise, very good exercise for you to check if you understood the proof of Lindeberg theorem. Assume that you have a sequence Kn converging to plus infinity. And now, instead of having these independent random variable, assume that you have an array. So for k equal to 1, you have from 1, 1 up to k1, you have in the first line k1 random variables, and they are independent. Now, on the second line, on the second row, you have x2, 1, up to x2, k2, which are independent random variables. And more generally, if you go to the nth row, you have xn1 up to xn kn, which are independent random variables, which means that on each row, the random variables are independent and no condition is made on different rows. The idea here is that in the first row here, you have sigma 1 divided by S1. In the second row, if I want to represent these variables in terms of this array, so in the second line, I will take x1 divided by S2, x2 divided by S2. So that will be x12, this x21, and this one x22. And at the nth row, what will appear? It's x1 divided by Sn, xn divided by Sn, and that will be xn1 up to xnn. And this is exactly the notation I used here, x and j, for j from 1 to n. So you see that these are exactly the notation I used. So now assume that you have for each row k, so for the nth row, kn independent random variable, and that these random variables satisfy the same conditions, which means that the expectation of x and j is equal to 0. So what you have to keep in mind is that x and j mean here, in our previous argument, xj divided by Sn. So x and j is equal to 0, and if you take the sum from 1 to n of the expectation of x and j square, then this is equal to 1. So you see, this is exactly what happens if you take these random variables, because you have expectation of xj squared, sigma j squared, divided by Sn squared. If you sum over j, this gives you 1. And so this is for j between I wrote here kn, but it's actually kn, right? And here it's j between 1 and kn. So let me erase that. So this, we have independence, we have expectation, we have that sigma j divided by Sn square, it's equal to 1. And now we need to translate this condition, but this condition, so if I divide that by Sn, what I get, it's and so if I change variables, this becomes and here I have now the distribution measure of the variable xj divided by Sn. So you have to check that this is equal. If here I represent the distribution measure of the random variable xj divided by Sn, and this will be our xjn, or xnj in our new notation. So the Lindbergh condition would be that now I don't have n random variables, but I have kn random variables, and it will be that the limit as n goes to infinity, and this for all epsilon, that the integral with respect to mu and j, that this is equal to 0. So what I claim is that the same proof shows you that xn1 plus xn kn converge in distribution to a mean 0, variance 1 Gaussian random variable. So if you have x1, so these rows of independent random variables, you have kn variables. Kn is converging to plus infinity. And besides that, they have mean 0. They satisfy this condition and Lindbergh condition, which is translated to that, then this result holds. So I would ask you to prove this theorem. And as I said, the proof is identical to the proof I gave you. Notation slightly different, you have to be careful, but it's a very good exercise just to check if you understood the proof to prove this theorem. So I'll repeat the statement. You take kn, a sequence which is increasing to plus infinity. Now for each n, you have independent random variables running from 1 up to kn. So these are independent. For each n, these random variables are independent. They have mean 0. They satisfy this condition on the second moment, and they satisfy Lindbergh condition. What I claim is that this sum converges in distribution to a Gaussian random variable with mean 0 and variance 1, and that the proof I gave applies almost identically to the present situation, which is slightly more general. So I leave it to you as an exercise.